If you go to Exam Prep and Homework Solutions, it's the 5th one down on the left. So this first post is going to help you with Exam 2. The outline, there's nothing on the exam that's not highlighted on that outline and that we emphasize in class, okay? Let me just point out that you are responsible for that proof of the arc length. So either reproducing the whole derivation of the arc length formula or understanding the principles within it. So I could ask about a part of it, could ask you to reproduce it, and you need to understand everything from the beginning to the end of that, okay? As well as using the resulting formula to find arc lengths, okay? But it's not just that, it's that derivation that I had you watch in the video, and I went over it quickly the next day, but make sure that you understand that whole derivation, okay? But the rest, so just basically we talked about using integrals to find areas of regions, volumes of various solids, arc length, and these physical applications. That's the bulk. That's the whole test. Okay. And then I gave you some bullet points so you know specifically what you're responsible for in each of those arenas. Okay. So that's the review outline. That's this kind of the centerpiece of your studying. Everything on the exam is mentioned in that review outline. Okay, so then I gave, a couple days ago, I put up a list of good practice problems from the book, and I tried to pick as many odds as I could so they had the answers in the back. But there are some evens that are important problems, so I put those on there as well. And then there is just a general 271 website that's here. Let's go there. That has more good practice, and it actually has practice exams, but I have written my own exam, and it looks totally different. It's not one of the practice exams with different numbers. It's definitely not that. But there's still good practice on those exams. So this is the 271 page. So there's a couple practice exams here. And then there's this. Now, on those practice exams, they have velocity, acceleration, net change. We did that in exam 1. We did that stuff in exam 1. That's not on our exam. So our exam review sheet has the comprehensive list of everything on your exam. So there's a little bit of difference between this 271 homepage. Okay, so you can ignore those in your studying. We've kind of already done that, so you don't have to study that. So you can check out the practice test. Again, I've written my own test, having never seen those practice tests. So there's good practice on there, but my test is not one of those with different numbers. Okay? And then some of these practice problems here, down here, applications of integration, that's where we're at. Some of them have answers, not solutions, answers, so you can check your work. Some of them do, some of them don't. So you got a lot of resources for practice. Questions on studying for the exam? We'll do what we did last time. We'll begin at 8:45. We'll begin at 8:45. And what we're going to do is we're going to do every other seat, and then we're going to start from the front and fill in every seat until we have enough. Okay? So if you're going to sit in the back, just know you're going to have to sit every other seat in the back half. Okay? Other questions? We'll go from 8:45 to 10:15. All right, so I'm going to spend today working on these. You've did the web work, and you've got lots of, hopefully dug in, and you're really working hard on these physics problems, and so it'll help you for me to do some examples now that you've got a lot of foundation, and hopefully now me doing some more examples is going to really help. So the first one I want to do is the inverted cone, the tank. And I also want to explore today the idea that you can do these problems with different frames of reference, meaning where you put your origin, where you put 0. Okay, and so we want to look at that, because if you're able able to do it, the same problem in two different ways, and you understand it both ways, then that's the best understanding. Okay, so we want to look at that. So we've got the tank in the inverted right circular cone, height of 5, radius of 4. So let's draw. Always draw pictures. Always draw pictures. Okay, and so the height is 5 meters. Radius is 4. That's the radius at the top. Okay? And it's filled with 4 meters of hot chocolate. And again, it's our blue hot chocolate. And we want the work to get all that out of over the top of the tank. So it's going to we're going to get all that. Oh, that's really bad, 5 meters. Let's see here. There we go. Right there? There we go. Okay. So, and we want to get all that hot chocolate out the top of the tank. So, what is this about? It's about a typical pancake of hot chocolate. Typical pancake of hot chocolate. And how much work it takes to get that out the top of the tank. So we're in a little bit of work, right? A little bit of work. And work is force times distance. What's the force? What's the force to lift something? It's weight. Weight is a type of force. And what are the units for weight or the units for force? In English? In English, that's in the metric. But in English, what are our weight or force units? Pounds. In metric system, what are our weight or force units? Newtons. Okay? So this is going to be newtons. So it's going to be the weight in newtons. It's going to be the weight in newtons. Or mg. No, not mg, because we have the density. So it's going to be, yes, it's going to be the density times g times the volume. So the density times g will give us newtons per meters cubed, and then times the volume will give us newtons. That's our force, and then times the distance. And all this is the weight of the typical layer in newtons. So now we got to decide our frame of reference. There would be two kind of most logical ways to do this. You could make, let's do it the first way is consistent with what we've done before. So let's take x equals 0 to be where we need to get that layer to. We're going to need to get it up to the top of the tank. So we'll say that x is the distance from the top of the tank down to the typical layer. That will be what we call our x. And then after we're done with that, we'll do it a different way. Okay? Set it up a different way. But this is kind of consistent with what we've done in class. And so our typical, so we've got the density is 1060. G is 9.8. So what's the volume? The volume is pi r squared. It's the volume of a cylinder, pi r squared delta x. And then what's the distance? So the nice thing about this frame of reference is the distance is simply what? I got to move that layer from where it is up to the top of the tank. That's exactly what we called x. So that's the nice thing about this frame of reference is it makes the distance that we're moving it to do the work easy. It's just x. So all that's left is what is r? R changes with x. R changes with x. R is radius, x is distance, and so we need to get a relationship of, given an x, what's the corresponding r? We need r in terms of x so that everything in our little work formula there is in terms of x. So when x is 0, what is r? And when x is 5, what is r? 0. So we need 2 ordered pairs. Now, we do this technique when we have a linear relationship between, right, the ordered pairs thing and finding the equation of the line or the linear relationship is when it's a linear relationship. There's other things, right? So you were given some parabolas, you have circular things. So it's not that you always do 2 ordered pairs and find the linear relationship. You only do that when you have a linear relationship. And that's because the sides of a cone are straight. Okay? R is varying linearly with x because the sides of a cone are linear. Okay, so we've got the rate of change is, looks like 4 minus 0, negative 4/5. And then we have the y-intercept is 4, right? So we have a 0.04, so we can just write down that r equals negative 4/5 x plus 4. And then we can test it. If x is 0, we get r equals 4. If x is 5, we get r equals 0. So we got it. So now we've got the there is the work required for the typical pancake to get it out the top. So we got to know what everything means. This is what? That's the weight density times the volume gives the weight. So everything in parentheses is the weight, which is the force. And work is force times the distance you're moving it through with that force. So that's your little bit of work. So let's set it up, get an answer, and confirm here. So we're gonna, okay, so then we're gonna integrate from what to what? So we're doing dx, we're gonna integrate from x equals what to x equals what? Well, that's a matter of the layers that we're moving, right? So we want to know what's the lowest value of x, what's the first layer that we're going to move. X equals what? 1, right? So when x equals 1, that's the top layer of the hot chocolate, x equals 1. So that's the first layer that we're moving out. And then until x equals what? It's like the very little teeny pancake that's like at the vertex at the bottom. X equals 5. Okay, so it's going to be x from 1 to 5, and it's going to be the 1060 times 9.8 times pi times negative 0.8 x plus 4 quantity squared times another x, right? Did I set that up right? Does that match what we did? I think it does. So it looks to me like, and so what are the units here? Do we have everything in newtons and meters? So that should be joules. Newton meters is the same as joules. That's amount of work. 8891,149. Right. 891149. 891149. I need new units. What are my units? I think that's capital J. Got it. Questions on this, using this frame of reference? We're going to do it a different way in a second here. Questions on doing this? Okay, so another possible frame, you could make x go down from the top of the hot chocolate. That would work. But I want to do something completely different this time, and I want to make x go from the vertex up. So x be from the vertex up to the typical layer. So this is going to be a new approach. And how would that change the setup? Okay, well, the force for the typical pancake would be the same. That has nothing to do with that, with how I'm deciding what x is. So, oh no, it does. So, sorry. So this is going to change. So we need a new relationship of radius and x. Okay, so we got to do that. So now we got this new relationship between the radius and what x is. So when x is 0, radius is 0. Okay? When x is 5, radius is 4. So this is an easier, basically you just have r equals 4/5 x. You got an easier with this frame of reference because you're basically putting your line through the origin, x equals 0, r equals 0. You have a very simple relationship that r is always 4/5 of x. Okay? So what are we going to have? We're going to have our 1060 times 9.8, because we're in metric, times the volume, which is pi. Now r is 4/5 x squared, pi r squared delta x. Okay, and now the other thing that's different will be, or another thing that will be different, so we've got a different, with that frame of reference, we have a different relationship of r and x, and we have a different distance that we're going. So now, for the layer that's x up from the vertex, how far do we have to move that to get it out of the tank? So we have to move it, the distance is this far. That's the distance that this layer is going, and how do we express that in terms of x? Okay, a couple of you are saying it up here in the front. Do you see that this whole distance to the top to the bottom is 5? If we want d, to get d, it's going to be 5, what? Minus x. So the distance now it has to go is 5 minus x. The whole distance from vertex to the top is 5. If we just want the d part, then we got to subtract what we called x, and then that's how far we're lifting the layer out the top. Okay, and then the last thing is the limits of integration will be different too. We're going to integrate from what to what. So all the layers of chocolate milk in terms of values of x go from what to what values of x. So that will be x 0 to 4. So how will this integral be different? Go down here. So now we're going to go from 0 to 4. 1060, so we had a different relationship. This time it was just positive 0.8x squared. And now our distance we're going is 5 minus x. Same exact answer. So when we change that frame of reference, we got a different relationship between r and x. We got a different distance that it has, or a different expression for the distance it has to travel, and a different set of limits. But it's all consistent. Since they're all consistent in that frame of reference, we get the exact same answer. Anybody have a question? Remember, on the exam, I'm going to give you variations on these. You're not going to have, it's not going to be a problem just like this one or just like the ones you did in the web work. New context. something a little different that you're going to have to apply the principles. Okay? I want to see if that you can that you learn something broadly, not just how to do specific types of problems. Okay? Questions before we go on to another one? Okay. Let's look at the dam. Okay, the dam problem. Okay, so here we are. So, yes, it is number 11. It's number 11 in the web work that you did. So we want to get the total hydrostatic force on the gate. So in terms of a frame of reference for this, again, we can use different frame of reference. For hydrostatic force, I recommend making the zero value the fluid, the top of the surface of the fluid. So we'll just do this problem one way, and that one way is that x is going to be down from here. Now the disadvantage to that, there's a great advantage to that in terms now x is exactly what the depth is, and we know that pressure varies with depth. That's the great advantage to this. The disadvantage is we're going to need the equation of this circle, and now it's not centered at the origin. So that's the trade-off. The trade-off is now that circle is not centered at x equals 0, but what will the equation of that circle be? Do you know the equation of a circle that's not centered at the origin? We should be able to do that. Equation of a circle that's centered somewhere other than the origin. X minus, call it A and B. X minus A squared plus Y minus B squared equals R squared. Okay, so what is our A and B? If we're going to do like, so basically we're doing this. And so if we're going to use x and y, so maybe it'll be easier to do it this way. Y this way and x this way. A little more consistent with what we're used to. So y will be up and down, but y will actually be positive going down from the surface, and x will be this way. So what is the equation of that circle for the gate, for the dam gate? X minus what? 0 squared plus y. So y is going to be positive going down this way, so it's going to be y minus 10, right? Equals radius squared. So in terms of we're going to do a typical horizontal layer of the force, right? And so that's going to be the width of that layer is going to be determined by the equation of the circle. It's not a linear relationship. It's a circle. Okay. But the center of that circle is at 0, 10, right? Y is positive going down, so the center of the circle is 0, 10. The radius is 2. Everyone get that? So we're going to look at what? We're going to look at a typical strip here and find the force on the typical strip. So a little bit of force, right? A little bit of force is, how do we say, is pressure times area, right? And pressure is density times depth. Okay, so we have that's our mass density And we need force density, so it's going to be 1,000 times the 9.8, because we're in metric. And then our depth is what? So in this situation, what is the way I've set up the frame of reference, what is the depth of the typical strip? It's just y, right? That was the advantage to doing this frame of reference, is that our depth is easy. It's the same thing as y. How far down you are is the same thing as y. Okay, so now what's the area of the typical strip? Well, that's a rectangle. So what is the area of that rectangle? It's going to be, back from our areas and strips and all that, what, in terms of our frame of reference with x and y, what is the area of that typical strip? What's the width of it? Is it x? 2x. Do you see that the width of the strip is 2 times x? Because x is our distance from here to here. This is x. Right there. So the width of the strip is 2x. And then what's the little height of the strip? Delta y. So is this going to be, are we going to write this in terms of y or x? Y, because it's delta y. So then all we have left is to get x in terms of y. Well, that was the equation of our circle. The equation of our circle will give us the x in terms of y. So density times depth times 2 times what's x in terms of y? It looks like the square root of 4 minus y minus 10 quantity squared. Times delta y. That's it. Got it. All that's left is the limits of integration. So that the little bit of force for that strip is this expression here. Questions on that? Okay, let's put it in and see how we did. And 800 y 2 square root 4 minus. In terms of solving antiderivatives on the exam, you're responsible for the basic techniques we learned for the first exam. This one would probably be out of that. Scope, because you would need, I wouldn't ask you to do an antiderivative like this one by hand, but all the basic techniques that we learned, straightforward techniques, you'll be responsible for, okay? But this one is kind of out of that range. Okay, something's not right here. So we need the limits of integration. What's up? Yeah. So what are my limits here? From y equals what to what?
From 0 to 12?
No, but it's the strips, right? What are the y values for the first strip that gives me a little force, and the last strip that gives me a little force? So if I said y, so my first strip is at the top here. Right there. So what y value is that? Is it 8? And then the y value for the very bottom of the gate is? So 8 to 10. Five, 6, 3, 4, 7, 8. I think this is also joules. We're doing everything in newtons and meters, right? This is also joules. 5, 6, 3, 4, 7, 8. Oh no, newtons is force. Sorry, this force. Here they gave us the units. Questions on this example? Hopefully this is helping. Now you've dug in, you've worked hard on these problems, and now you're watching me do some. This is hopefully shoring up the little deficiencies you have. Okay, so I have another really good problem. Any questions before we go on? Okay, here we go. An oil tanker has a cylindrical shape with a diameter of 12 feet and a length of 74 feet. So it's a cylinder lying on its side, like on a big truck. Okay, it's filled 3/4 of the height with gasoline that has a density of 44.9 pounds per foot cubed. Two things: find the total force of the gas on the vertical circular side of the tank, and then how much work would be required to remove all the gas from a valve at the top of the tanker. So now I'll draw the picture for you. You should be able to draw this picture, but for time's sake, I will help you draw it, and then you'll be off, okay? We want to get this done, and we want to hopefully also do this with a couple practice the different frames of reference, okay? But basically, the end of it is a circle. Like this, and then it's sitting on the truck bed. This is supposed to be the wheels of the truck. Something like this. And so it's filled up with 3/4 by height. With gasoline. Okay, and so what do we want? We want the hydrostatic force on the vertical circular side. Okay, and then we want the total work to remove all the gas, say, out. So they actually do have they connect the hose to the top in some situations, I think. So we want to get all the gas out the top. Okay, so through a valve or whatever out the top. Okay. So let's see how much. So see if we can work efficiently, because I do want to get to, like I said, trying different frames of reference to solve the same problem. So working on that, because that really, we're going for the best understanding of this. Okay, go. So 2 tasks. And so work on whatever one you think you're having a little more trouble with. If it's the hydrostatic pressure, work on that one. If it's work on the work one. Okay? D is what? 3 minus y. Area is 2x delta y. Okay, questions on part A. So I did here's two different frame of reference. First I did that the water level was y equals 0 and positive y was down. And what's the advantage to that? Well, now y is your depth. That's what the advantage to that is. That's similar to the gate problem. Then I put the origin at the center of the circle and I made y pointing up. What's the advantage to that? The circle is easy. Circle, that's your easy, but what makes that hard is getting the expression for the depth. So the depth of a typical layer then is from here up to the surface, which is that black length I've described right there is 3. That's 1/4 of the diameter. So the diameter or the depth would be 3 minus y, because y is this coordinate right here. Y is from there to there. That whole thing is 3, so the depth is 3 minus y. Then, now your 2x, the x is a little easier because of that equation of that circle, delta y. So here are two possible setups based on 2 frames of reference. So I may tell you this is the frame of reference you have to use. So it's important that you can do this both ways. Yeah. Nice and loud. Nice and loud. What's that? Are you talking about this? The depth on this one? You think it should be y minus 3? Is that what you're saying? I can't hear you. But it's 3 minus y, so I don't. The first one, sorry. Because if I put the origin here, the center of the circle is down is at 0, 3. So I put the origin of the axes is here, 0, 0. The center of the circle is in the positive y direction 3 units. So remember that equation of my circle is x minus a squared plus y minus b squared. By putting y equals 0 at the top of the surface of the gas, my center is in the positive y direction 3 units, 3 feet. You see it now? Nice and loud. Oh, because this is just the force on the circular plate. It doesn't matter how long the tanker is. That force, the pressure will be the same no matter how much gas you have. So the force will be the same. That will come in the work. So what's your typical element for work? What are you lifting up out of the tanker for work? What's the shape of it? They're rectangular layers. Rectangular layers whose width is determined by the equation of the circle. So when you did the work problem, your volume should have been length times width times height. It should be, and that's where the length comes in. I'm going to do those. I'll make a video doing part B, and I'll tack it on to today's class video. Hold on, question.
On part A,
Yeah.
about the constants, you have y minus b squared. How would you actually go about this?
You're talking about the antiderivative?
Yeah.
You would need to do a substitution and maybe use, so you do a substitution, and then you have two integrals, and one would be doing the chain rule, and the other would be a table. That's why I'm saying that would not be fair game for the test. That's a little bit too much for the test. Because the first layer down here is the radius down. So that's the first layer, and that's at y equals -6. And then the top layer is at y equals 3. Study. See you Friday early. 8:45 to start the exam.
So I have a question on, you know how you said when it's like forward, I don't care how it's like how long.
Right, that's right.
So like why?
Well, I mean, think about the ocean.
Oh.
Is there more pressure because the ocean goes miles and miles and miles and miles out?
Because they're the same.
Yeah, the pressure at a certain depth in a swimming pool is the same as the pressure at a depth in the ocean. Doesn't matter how much width of water you have. Because it's about the water that's above, right? The pressure is about the weight of the water above a certain point, not out to the sides.
Okay.
So that's the same principle here. The length of the tanker doesn't matter.
They would still be the same force, like
No matter how long the tanker is, you have the same lateral force on the end of the tanker. And that's the same principle as swimming pool at 10 feet down in the swimming pool. It has the same water pressure as 10 feet down in the ocean.
Okay.
Because the ocean goes on forever, right?
Yeah. And I like a question. So do you know how like sometimes you do like
So let's draw the picture again. Okay, and then this is going back this way. And we got D equals 12, L equals 74, and rho is 44.9. Okay. And now we're going to, and again, it's 3/4 full by height. So again, that's going to be 3 feet up. That'll be 3 feet up from this horizontal diameter, or 3 feet down from the top. And if our opening here is at the top like this, then in terms of the distance that we have to move every layer, in terms of calculating the work, let's put our axis this way. So we're going to put kind of similar to what we did before with that last example with the pressure. So now that's going to be, again, positive y down, and then x to the right. And this is going back into the page like this. And that's that distance of 74 feet back into the page. So we'll cut it off there, but we know that it's just gonna go back 74 feet back that way into the page. But in the screen here is our plane. It's going to be x this way and y down this way. Okay, so, and the reason I want to do that is now the distance that any layer has to move is going to be y again. By putting the origin at the height of the opening, now when we have our typical layer, we know it's going to be, work is going to be force times distance, so we're going to get the weight of that layer. The distance it's going to go is going to be the y coordinate. All right, so let's take a typical strip here. But it's actually not a typical strip. What is it? It's a typical layer of oil. So now now this 74 feet comes into it. And so we're going to have this layer of oil, and we've got to move it, what, a distance of y. So if we set that up here, so basically we have so it's going to look like that. That's going to be a typical layer, and so we need to find dW. dW is going, or delta W is going to be force times distance. That force is going to be the weight of that much oil, the weight of that horizontal layer of oil. So to get the weight, it's going to be the weight density times the volume. So the weight density is going to be rho times length times width times height. So that's going to be, because it's a rectangular layer, rectangular solid. So the force is density times volume. And now the distance, since I set my y equals 0 here, the distance it has to move is y. That makes that easy by putting that our origin at the place where we've got to get every layer to, then that distance that it has to travel is simply y. Okay, so we've got our 44.9. Okay, the length is our 74 feet. The width is 2x. And the height is delta y. Okay, so now what's x? So x is the x coordinate on the circle, just like in the last example, just like on the pressure part. So x is the x coordinate on the circle, and the width of our layer is 2x. Okay, so what do we need? We need the equation of the circle. Well, now if our origin is up here and positive y is this way, then that means our center of our circle is going to be 0, positive 12, positive 6. The whole diameter is 12. We're starting from 0 at the top. Now the center of the circle is 0, 6. And so the equation of the circle, center 0, 6,
radius 6. That equation will be x minus 0 squared plus y minus 6 squared equals 36. And again, we need 2x. We need 2x, and so we're going to solve this for x. And so this is going to be our delta work. It's going to be 44.9 times 74. That's the length of this way, that's the length. The width is 2x, so times 2. Solving for x here, 36 minus this, square root. Times the height of that whole thing is the volume. So length times width times height is the volume. Volume times mass density is the weight. So that's the force. The force to lift something is its weight. Okay, and then times the distance it's going to go. Now, because of the way we set up our system here, the distance it has to go is simply y. Okay, and then we're going to go, the first layer is going to be at y equals positive 3, and then the last layer is going to be at positive 9. So we're going to do the total work. It's going to be the integral from first layer 3, last layer 9 of dw, which is this thing right here with a dy instead of a delta y. Mass or weight density times volume gives force. The weight of an object is the force required to lift it. So this is the force that's going to be required to lift that layer. And then times the distance that we're going to apply that force gives us the total work, and the distance is simply y because we set up the origin there. So then from 3 to 9 of that. Okay, I hope it helps.